This is Professor Antonio S. Marahas, and this is Advanced Digital Technique. So we go now to NAND gate. NAND gate is sometimes called the NOT AND gate. Okay? So it is actually a combination of an AND gate and an inverter. So we define NAND gate as a gate with two or more input signals, again with only one output signal. All inputs must be high to get a low output, and that is a definition for the NAND gate. So for the symbol, so we have here an AND gate with two inputs represented by A and B again. And then we have here an output which is connected to our inverter. So the output of the AND gate is A times B. Okay? Once it passes through an inverter, your Y becomes A times B complement. That is our two-input NAND gate. No? The symbol for our two-input NAND gate. Okay? Now, how about the truth table of our NAND gate? The truth table, by the way, represents the operation of a particular gate. So, for example, in this case, you have the NAND gate. So, the truth table represents how the NAND gates operates. Okay? So, you have here the truth table again. So, you have inputs A and B, and you have here the output represented by Y. Again, the combinational values of A, B are 0, 0, 0, 1, 1, 0, and 1, 1. Okay? And what will be our output? So, according to our definition, all inputs must be high to get a low output. And that is in this particular condition. No? A and B are both 1 or high to get a low output, 0. The rest will be 1. So, if you notice that in our NAND gate, it is simply the opposite of the AND gate. Because according to our definition for the AND gate, it says all inputs must be high to get a high output. So, in our AND gate, the output here is 1 and the rest is 0. This is our AND gate output. Now, if, for example, if your input here, A and B are 0, 0, the output of your AND gate here is 0. Once it passes through an inverter, it becomes 1. Okay? And then you have 0, 1. 0, 1, the output of your AND gate is 0 again. Once it passes through an inverter, it becomes 1. And so as with this particular condition. Once you have 1, 1, supposed to be in your AND gate, the output here should be 1. But once it passes through an inverter, it becomes 0. Okay? That is our two-input NAND gate. Okay, so let's have a three-input NAND gate. So you have here the symbol. Again, we have an AND gate with three inputs represented by A, B, and C. And then you have here an output which is connected to your inverter. Okay? So the output here is A times B times C. And the output Y here becomes, once it passes through an inverter, becomes A times B times C complement. Okay? So, the other symbol for a 3-input NAND gate is this one. So you have an AND gate. Okay, again represented by A, B, and C. Then you have here a bubble at the output part of your AND gate. So your output Y here will be A, B, C complement. Okay, so the bubble here, take note, should be directly connected to the output part of your inverter. Dili na to siya parehason ani ato ang inverter diri nga nasa layo. It should be at the back of your AND gate symbol. Okay? So for the truth table, again, this will define how our NAND gate operates, no? So truth table for the 3-input NAND gate. So you have again inputs A, B, and C, and you have an output represented by Y. So what are the combinational values again of A, B, C? You have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay? Then, according to our definition for the NAND gate, all inputs must be high to get a low output. So, it is in this particular condition that all inputs are high to get a low output. Okay? The rest will be 1 or high. Okay? So again, the NAND gate is simply the opposite of the AND gate. So whatever the output of your AND gate, once it passes through an inverter, it becomes inverted.